So my presentation is actually a continuation to what Sotonic said and also what Laura discussed like a couple of weeks ago. And it's related to the way that to actually the concepts that we use to solve those equations. Laura discussed that how we derive those equations, equations describing different phenomena in engineering. And Sotonic discussed the way that we can use basics of mechanics to describe things in biomechanics and mechanobiology. And in this presentation, I want to discuss that, okay, in the end, how we use computers to solve those equations. So the things that we discussed, actually the questions that were originally asked, was like, what are those colors that come out of the simulations, and what are those lines, those triangles that you see on typical output of computational models, and why we use what is the concept of finite element first, and why we use finite element to solve these equations. But instead of discussing these things, I decided to discuss another important concept that by understanding it and by seeing the purpose of that in engineering, you can get the answer of all these questions. And that's actually the concept of approximation. And this is what we are going to discuss today in this presentation. But before that, there is something here very important to emphasize. Actually, Sotonic pointed to that. But that's actually the question, is finite element modeling only for mechanics, or let's say solid mechanics, or not? Actually, you hear this term mostly from people doing solid mechanics or biomechanics stuff, but the truth is it's not limited to solid mechanics. It can be used for any other things in mechanics or even outside mechanics, like fluid mechanics, for material science, for chemistry, for mass and heat transfer, or let's say, literally speaking, anywhere that you have an equation to solve or differential equation to solve. This method can be used to solve equations. And in the next slides, I want to show you some examples. Actually, I want to show you the equation. As I said, I don't want to discuss the equations. I just put the equations to show you that these equation results will lead to these results. For example, in this case, for fluid mechanics, Navier-Stokes equations results to the results of fluid flow. Just to show you that, these are the things that we can do with finite element. So this equation is solved in finite element 2D, and you can see that the flow inside a pipe. And the colors, as shown on the color bar, they demonstrate the velocity magnitude. So whenever it is red, it's higher velocity, and whenever it is blue, it's lower velocity, close to zero. And then particle trackings also visualized. And this is something that I've showed you several times. That is actually the corrosion process. Colors here demonstrate the release of material, the concentration of mass, in this case, magnesium ions, and the equation that describes this phenomena is on the left. And when we solve it with finite element, we can get these results over time. This is another example for cell viability. We put group of cells inside a placeholder, inside a medium, and then they start to consume oxygen. So what you see here as the colors are the oxygen concentration, and the phenomena is described by the equation on the left. So you can see cells start to consume oxygen to survive. Again, solved with finite element model. And this case, this is tissue growth on a scaffold. So scaffolds are not visualized here, sorry. So the spaces that you see, those canals are actually scaffolds. We put cells and they start to grow. Again, solve with finite element model from the equation you see on the left. And this one is the one that Sotonic showed it for the effect of shear stress, but this in this case is inside a perfusion bioreactor, but it can be also outside of that. As you can see in the middle, over time, we want to see how it grows, how cells grow, how new tissue is formed on a gyro scaffold. And equation is what you see on the left. So we solve this equation and we get these results. And it can be also applied to multiphysics problem when we combine different physics, different phenomena together. In this case, for example, we combine diffusion with Navier-Stokes, leading to a result like this. You can see how nice this equation can describe this phenomena. On the left, we have low diffusion, on the right, high diffusion. We solve the equation and we get this. This is another multiphysics problem that is related, which is called heat, let's say forced convection. We have heat exposed on those circles and then a fluid flow from the left to right. And then it's, the convection just takes the flow and then you can see the behavior and the pattern. Described by combining Navier-Stokes equation and diffusion, heat diffusion actually, or heat transfer equation. So these are all examples, not solid mechanics, but you see that we used finite element to solve them. But there is one thing before I jump into the discussion of approximation. There is one thing to address here. You may ask, what happened to those lines and elements and triangles? The answer is they are always there, but we usually do not visualize them for having a more clear image or output or video. But for example, in this case, if we put a material beside a medium, it starts to degrade, pH changes on top of it. You see that this is a solution that you see when someone presents a finite element model. But the actual image is something like this, that we have the nodes, we have the elements, and actually the equation is solved on those nodes. We will discuss this later in this presentation. But these lines and elements are always there. This is another example for formation of, side corrosion products on a scaffold. You can see that they are exactly the same thing, showing the same thing, one with elements, one without. But actually, you usually see that there's the figures on the left. And this is another one showing the original setup with those elements, with those triangles. And then on the left, this is actually the cell viability thing that I showed you, but for a single islet. And then you see that it's the consumption of oxygen without those elements, but actually the lines are always there. So these were just examples that, this is what we do. And then here, we want to start to see how we do that. So we want to see how we solve those equations, the equations that I showed you, describing, different phenomena, like for fluid flow, for, concentration of oxygen, for growth of tissue. We have the equation, and then we want to see how we can solve them. So the answer is quite simple, that no one can solve those equations because they are impossible to solve analytically, or, we cannot solve them. But then how we get those results? The answer is we can approximate the solution. So what I've shown you on the previous slides, they were just approximations of the real solution of those equations, but they were acceptable approximation. That's something that we will discuss later. But why approximation is acceptable? The truth is, we live in a world of approximation, and engineering is built on approximation. And not only engineering, but also, a lot of things on life around us is built on approximation. But approximation, causes loss of data for sure. But then the question is, who cares? As an example here can be like, this session started at 12:30. But who cares if it started at 12:30 plus 10 seconds or plus 20 seconds? Roughly speaking, we say that it starts 12:30. And in some cases, depending on culture or people, it can start, a couple of minutes even later. But still it's 12:30 with approximation. No one cares if there are some extra seconds. And that is actually what approximation means. One example more related to what we want to discuss. Just imagine that we have a circle here with a radius of 1. And then we are asked to, for example, cut a slice of it that is, divided by a line with 45 degrees. So the arc of this length, that is pi divided by 4. But let me tell you that no one can calculate the length of this arc precisely. We can always approximate it depending on the value that we choose for pi. And in real life, for example, if someone asks you to cut a ribbon with this lens, with this, red slice, red arc, that's actually the width of the blade of the scissor that determines the accuracy. So it doesn't really matter what value you choose for pi. Approximately it's correct and it fits the application that you want to have. But precisely speaking, or scientifically speaking, mathematically speaking, the length of the arc cannot be calculated. So the same thing, using the same concept here, we can apply it to, the topic that we had, solving equations. But in this regard, you'll see common applications of approximation in engineering. I want to mention a couple of them and discuss them in later slides. The first application is finding the roots of a function. That's a very trivial application of approximation. And then we can also find maximum or minimum of a function, and also finding the function itself. So for now, let's forget about the last two and focus on the first one, which is more intuitive, finding the roots of a function. So for that, let's solve some equations together. So everyone knows how to solve this. The answer is x equals 2. But another way to look at this equation is actually having a function constructed of it, and then we want to say what is the root of the function when the function is 0, x equals 2. Another way to face this problem is by drawing the function here and see where it intersects the x-axis, and that's the root of the function. Let's make the function a little bit more complex. So something like this. This equation can still be solved analytically. We know how to factorize it, and then the roots are 1 and minus 2. And graphically representing, you can see the roots there. Let's make it even more complex, something like this. Still, we can factorize it. It's a little bit more difficult, but obviously we can see that the roots are 1, minus 2, and 3. And on the graph on the right, we can see that they are there. But if we make the equation more complex, like in the order of 5, fifth order, it becomes really difficult to solve. And that's where we say that we cannot solve this analytically, although we can see the roots on a graph. But that's not what we are looking for. The graph is here for demonstration purposes. So we cannot solve this analytically. And that's where we should do some approximation. And instead of approximation, we can say that we want to do some numerical modeling, or we want to use some numerical methods. So, there are lots of things that we can do here. But before that, let's imagine that the function is actually a black box. We have a complex function. We don't care how it works. We give it an input, like x in this case, and then, for example, we say x is 0, and then it tells us that the output is minus 1. So we have a black box, and the question is, we want to see where this black box produces 0, because we want to see the roots of that function. So with this, assumption, let's go for one of the most beautiful numerical methods called Newton method or Newton-Raphson. You hear this term a lot, probably from us in our presentations, but this is actually how it works. And we want to use that to find a root of a function. Let's assume that the function is this red line. We don't know it. It's here just to visualize how Newton method works in action. So the root is here, obviously. But then the method says that we start with a guess and we get close to the answer, to the real solution, step by step. And in this way, we approximate it. So let's start with an initial guess here. The method says that on that initial guess, we draw a line tangent to the function. This is something that we discuss later, that when we don't have a function, how we can approximate this slope. But for now, assume that we have the slope. And then the slope crosses the x-axis again, And that will be our second guess. And we continue this procedure iteratively, step by step, and you will see what happens. So this is, the second slope, the next guess, and then the next one here, again here. So you see that now it throws us to the next side of the graph. Again, we continue that, and now, wow, we are getting close to the solution, you see. And actually, we are almost there. And if you zoom in, we're still not there, but you can see that we can continue until we get close enough to the solution. And this term, actually, I don't know, I don't remember exactly. I read a paper about this. I think Lisa actually shared it on Twitter or not on Slack, that the concept of close enough, this is very important in engineering, that how you define it. And that's actually also defines the approximation, that we stop at the point that we get close enough to the solution. And there is another term here called convergence that you hear a lot from people doing numerical modeling stuff. That we did this and we converged to the solution. And that's actually the concept, that you see that we get close to it iteratively and a solution converges. But in some cases it could be divergence or lack of convergence. When people talking about convergence, that's actually the concept. But then the question, as I said, is we don't have the function itself, how we can get the slope. I think the answer is very obvious. For engineers, they always approximate things. So they can also approximate the slope of the tangent lines. That's not difficult. And there are lots of methods, again, in this regard, but I will describe one of them here. So let's zoom in to one of the points that want to have the slope. So this is the function that we don't know. We have only a black box telling us the value at different points. And we want to have like the slope of the function here, xm. I call it xm, this is just a name. It doesn't mean anything. We know the value of the function at xm. So we go a little bit, and we want to have the slope here. So we go a little bit backward and a little bit forward. Let's call this difference. I intentionally use the terms difference because later on you will see what that means. Let's call this h. And we can always ask the black box to tell us the value at xm minus h and plus h. And then I connect these two lines together, and you see that the slope of the new line, which we can get, is the same as the slope that we wanted to have. So with this way, we can easily approximate the slope. And this is actually what we use in the Newton method to get the slopes at the points that we wanted to go to the solution iteratively. And this term, I just want to mention the technical terms here, just, to map it to the concepts that you hear from us. This is called central differencing, going a little bit forward and backward and connecting them. And that was first order because we use only 1 point backward and 1 point forward. If we use 2 points on both sides, it will be second order and so forth. More accuracy, let's say. But there is also, another thing here. If we assume that h is very small, we get close to the central line, we can always use only 1 point. Because if h is very small, then the slope will be approximated the same with just 1 point. And that's the concept of backward and forward differencing. That is also something very common to use, and it is less expensive, I would say. Talking about cost, because we need to evaluate, we ask the black box to calculate the value of the function only in 1 point instead of 2. So that was the concept of approximation for finding roots of functions. But then what about finding minimum and maximum of functions? This is called optimization. Already Fernando gave you a nice presentation on this, that how it works. If you remember the ball and the heel and the way that you move the ball to reach the downhill, the minimum of the function. But this is also, in this regard, approximation plays an important role. You may have heard about gradient descent. That's, a famous, very common algorithm used in machine learning. And these things are still related to approximation. But the thing that we want to discuss here, actually, back to the first question that we had for finding the solution of those equations, is actually finding the function itself, when the function is actually the solution that we want to seek for. And what that means, let's have another example in tissue engineering for cell growth. You put cells on scaffolds and they start to grow. So in this case, if you want to represent it as, a geometry and a function, it would be like this. Assuming a container, we put cells on the left and the bottom side, and then they start to grow. So we define a function, in this case, concentration of cells, denoted by C, which is actually a function of X and Y, because we can have, different concentration or different regions of this. But it is also, as you can see here, that on day 7 we have something, day 14 we have something else. So this is also a function of time. So actually C is a function of space and time both. And if we can formulate something that tells us how it grows, like a curvature-based model like the one that you see here, then the question is actually how we can find C according to the behavior according to its behavior. And that's actually what Laura discussed in her presentation. And I think by knowing that, by seeing that, we want to guess a function based on behavior, now you know what we are talking about. And we are talking about differential equations. So in differential equations, the equation itself gives you the behavior of the function, and we want to see what the function is. So how to deal with this, how to proceed? Again, we want to use approximation to solve this. But then we should answer one important question. That do we need to know the solution everywhere in the domain, every single point in the domain, or it's just enough to know it on a certain number of points? For answering this question, let me give you another example in tissue engineering for cell viability. As I discussed, we put group of cells inside a well, and oxygen supply is provided on the surrounding. And then we want to have like a function defined, C here, as I showed you, function of X, Y, and T in 2 dimensions. And the concentration of oxygen, so this function changes due to consumption and diffusion of oxygen. And then the research question is whether the cells survive or not. So the typical output of this simulation would be something like this. You see that it starts to consume oxygen, and based on the threshold that we have for example, hypoxia or death of cells, they can survive or not. But then how we solve this, let's have a closer look at the geometry. So this is the initial geometry that we start with. And we want to solve the equation, assume that we have the equation. I showed you the equation in the beginning, but it doesn't matter how it is. But let's assume that we want to solve the equation here. So instead of solving that on any single point you see here, which is actually the number of points can be infinity constructing this geometry, the modelers usually considers picking certain number of points like this on the whole geometry, and they pick more points close to the regions that are more important to them. So in this case, we put regions, more points, let me show you once more points on the surface, on the islets, the group of cells. So more points there, and then we use these points to solve those equations. Actually, we solve those equations only on these points. And then what you see as elements, we call it a mesh or a grid in finite elements or other numerical methods. That's actually connecting these lines together. As simple as that. So what you see is actually the points connected to each other. And then we solve the equation here. So it becomes something like this. The concentration of oxygen due to the consumption of it. And then we just omit the lines. And then this is what you see in presentations when we present something. This is actually the solution. And when it is over time, that will be similar to the animation that you saw in the previous slide. But there is also one important thing here, another thing, and the difference that you see between these two figures. On the left, as you can see, actually the one on the right is smoother. And the reason is on the left, you see that each triangle has only one color. And on the right, you see gradients inside the elements. And the reason is, here, we can say that we actually solve the equations inside these elements, these triangles. And that's why each triangle has only one color, demonstrating the level of oxygen. And in this case, each point is used. We call them nodes. Each node is used to solve the equations. And as a result, you can see that this node has a color of yellow propagated on the surrounding, and this one, and this one, and this one. So every node has its own value. And this is actually the order of solution, we call it. So in this case, we have solved them, on nodes, in this case on elements, and we have even higher orders in which we employ even more nodes inside the elements or on the edge to solve the equations. So let's go back to the question. Now we know that the answer to the question is no, we don't need to know it everywhere. And for the second question, yes, it suffices to know it on a certain number of points. But here I want to change a word, paraphrase a word to something else. Instead of certain, I want to use the word finite. And now I think you know where we want to go. The term finite has come into play. And it means, whenever you see it, it means that we want to approximate the solution of an equation on a finite number of nodes, points, elements, regions, parts, whatever. But that's actually what that means. And there are lots of different techniques that work on this basis. And finite element method is only one of them. We have like finite difference method, finite volume method, and much more, like method of lines, boundary element method. And you hear finite element just because, in our group, part of the group is actually located in the Department of Mechanical Engineering. And because, as I said, for solid mechanics, finite element is more convenient than the rest. And biomechanicians usually prefer to use that for their simulations. You hear this term more than the others. But then, for example, Department of Material Science, Chemistry, Physics, is actually, you hear finite difference, finite volume as many as, finite element. So that's it. But then very quickly, I want to show you, I don't want to start with the way that I did that for finding roots of functions, because with differential equations, we can always find the solution analytically. But I just want to start with an equation that cannot be solved analytically. We need to approximate a solution, and that's actually the example that I want to show you is a linear convection equation. So this equation describing how this quantity C is convected, is actually pulled by a fluid flow, and it's a function of t and actually time and space. So the solution will be something like this. If this is the blue line, is the initial state. After a while, in this case, it says after 10 time steps, I will describe the concept of time steps later. It will come here because it's actually pushed towards right. And in 2D, the equation will be like this. And this is actually kind of, output for that. When you see these kind of results, you usually expect it to spread around. But here we don't have diffusion term, so it just moves. So that's actually the concept of convection. And then we want to see how we can use finite element, or generally speaking, numerical methods to solve this problem. So we start with, one of the derivatives here. So the first one, and this is actually derivative, differentiation, slope in mathematics. So it's related to the slope. We can see this as, the equation is describing the slope. And we want to see what is the value of C, in this case in one dimension, along the x-axis. So we divide this length into a finite number of points. That's what we said for the term finite, with the distance of h. So now you can see the analogy for approximating the slope. And then we can start with one of these points and then get the value of the others based on the definition of a slope, approximating the slope, and the behavior that the equation is telling us actually. And that's where, the term that you've heard about a lot comes into play, boundary condition. And it says that, we know the value of the function at one of the nodes, which are usually on the boundary. In this case, it can be this one. So we know the value of c at x1, and using that and the behavior of the function defined here, we can calculate the value of c at x2, which would be something like this. It's actually approximated. And based on this one, do you remember that we can use 1 point to get the value of the other one, which was actually forward or backward difference? We can get the value of c at x3, and using the same principle, we can obtain the values of the rest of the points. So we have the value of c at certain number, finite number of points, and we can have the behavior of c or value of c all over it. And in this case, we say that we have discretized the space into certain number of points, and we have approximated the solution on them. So this is actually what you saw on those points on, for example, on a veil. This is actually what is happening behind the scene. But then we have another thing here, evolution over time. And for that one, it's also pretty simple. Similarly, we can assume that we have a new access time, and that's where another concept should be considered initial condition. That what is the initial state of the system and how it evolves over time. So in this case, we assume that the initial state is just 0. And then we constructed this red line based on that. So this red line, we can assume that is the first time point. And then similar to these points that we had along the x-axis, we can say that along the time axis, we have a second point with the step size of delta t, we call it time step. And then we can evaluate the value of c at a new time point, and it will be the next one. And this is the way that we can measure and we can study the evolution of the system over time. And this is actually all the videos, all the animations that I showed you, they were something like this. And to be, just mentioning the name, this is called explicit Euler. So as I said, there are a bunch of other methods, in this case infinite difference, that you can use, but this method is called explicit Euler. And it's explicit because we use the value of the previous node to compute the value of the next one. And for just one slide to talk about the approximation using finite elements. In finite element, the concept is very similar, a little bit different. And this is a brilliant idea that people invented in the 60s, that how we approximate a function. In this case, this is step-like function, the green one. We want to approximate that. So we again divide the space into finite number of points or elements. And then instead of taking advantage of the concept of a slope or numerical approximation of the slope, people here use a set of functions. Here, for example, 9 functions, I think, plotted in different colors. And then at each point, you can see that these, there is only, for example, at this one, there is only one of these functions that is non-zero. So in this point, you see that it's just this red one, here is the purple one, yellow one, here is the black one, and so on and so forth. And then the question is how we can use the value of these functions to approximate it. So we adjust these points, we can bring them up and down, very similar to the concept of equalizers that you have in music players or for music mixing. We can change the value of these functions and this node to approximate this function. This is a brilliant idea. There are a lot of theories behind it, but this is the core concept of that. And in finite element, people call these functions shape functions. You may hear this term also from modelers, and a choice that you make for these shape functions plays an important role in the solution that you get for approximating the function or approximating the differential equation. So here you see that we can choose this one as a 7th order, so choosing 7 functions to approximate a function. This blue line is the approximation, and here we use 14 functions to approximate that more precisely. And then the final note to mention is actually how this is very important, that how make sure that the approximation is acceptable. And the fact is, approximation makes the system and makes the models sensitive. So we should always measure this sensitivity. And for doing that, one of the techniques called VVUQ, you may have heard of. Verification, validation, and uncertainty quantification. This is actually where it should be considered, especially for verification. Verification deals with the level of acceptance that this approximation has actually for example, approximating the behavior of functions, getting the roots of functions, or solving differential equations. So this is actually very important. I think in later sessions we will have more discussions on this stuff. But yeah, so that's actually what I wanted to say. And as always, I always say that if you are interested to see more details, there are dedicated videos on Tux Writers. There, I describe more details of these methods for finite difference of finite element. In this series, Introduction to Applied Numerical Computing, and on this one for finite element modeling, in which I construct a problem step by step from the beginning, from building a geometry, meshing that, and then solving the equations using different software tools. So you may refer to these videos for more non very high general overview of these topics. Yeah, that's what I wanted to say. Thank you so much for your attention.